Why do we need reactive power compensation? How much should we compensate? The content is a bit long, please be patient and listen. As shown in the diagram, when the voltage U is applied across the resistance, the current I flows through it, directed to the right and clockwise. Then the power S equals UI. This is its apparent power, measured in units of voltamperes. What is apparent power? After everyone finishes listening, you'll have some understanding of the concept. As for the resistance component, the phase of the current and the voltage is the same. Assuming this is the direction of the voltage, then the direction of the current is also upwards. Their angle is zero. As shown in the diagram, the black line represents the voltage as a sine wave, and the red represents the current, which has the same phase as the voltage, but the amplitude may not be the same. We've drawn it smaller for ease of distinction. We know that the power equals the voltage multiplied by the current. Let's take the resistance as a reference. If P is greater than 0, it means energy is absorbed from the power source. If P is less than 0, it means energy is released back to the power source. Let's take a look at a cycle. It can be divided into two regions. In this region, the voltage is positive and the current is also positive. Multiplying them, P is greater than 0, absorbing energy. At this time, with a positive bottom and a negative top, the current is clockwise. This current is provided by the power source, flowing from high to low. The resistance absorbs the energy. Let's look at the next region. At this time, the voltage is negative and the current is also negative. Multiplying them, P is greater than 0, also absorbing energy. At this time, with a negative bottom and a positive top, the current is counterclockwise. The current is still from high to low and is provided by the power source. The resistance still absorbs the energy. It can be seen that the entire process absorbs energy, and this energy is consumed. It is used for work, such as generating heat. It is irreversible. For this type of irreversible power that has been consumed, we have given it a name called active power, represented by P. The energy absorbed is entirely used to do work. Therefore, for this load, P equals S, which means active power equals apparent power. The unit of active power is generally expressed in watts. What is reactive power? Reactive power is demonstrated in an inductive circuit with a voltage U and a current I. The power S also equals U multiplied by I, and inductive components hinder changes in current. Note that here it's hindering, not preventing. Current lags voltage in an inductive circuit by 90 degrees. Let's take a look at the waveform. Black represents the voltage waveform, and red represents the current waveform. This is a purely resistive circuit where the current lags voltage by 90 degrees. Now let's look at power. Let's examine a cycle. In the first region, with positive voltage and positive current, P is greater than 0, indicating energy absorption. Current decreases from high to low, which is clockwise. Then, moving on to the next region, voltage is negative while the current is still positive, and P is less than 0. The product of a minus and a plus gives a negative, indicating energy release. Although the polarity of the power supply has switched, the direction of the current remains unchanged, moving clockwise from low to high. Obviously, at this point, the voltage across the inductor is higher than that of the power supply. The inductor leads the current direction and energy is transformed from magnetic energy back to the power supply. As the energy in the inductor decreases, the power supply takes a dominant role, meaning it can hinder but not prevent the change in current. For example, in the next stage where voltage is still negative but current also becomes negative, the product of the negatives gives a positive P, indicating energy absorption. The direction of the current now changes to counterclockwise, from positive to negative. At this moment, the power supply is releasing energy. Inductors absorb energy, so during the final phase, P becomes less than 0 as energy is released. The polarity of the power supply switches, yet the current remains counterclockwise. Let's examine these for regions. It's clear within a cycle that energy is absorbed twice and released twice. The inductor itself does not consume energy, it stores energy as potential energy and is a storage component. For this type of power that does not perform work, we have a term, reactive power. It only facilitates energy exchange. For an inductor, electrical energy turns into magnetic energy, and then back into electrical energy. It consumes no energy at all, but is purely reactive power. Reactive power is represented by Q. In regard to inductors, Q equals S, typically expressed in units of VAR, which stands for voltamperes reactive. Now, why would we need to compensate for reactive power? Reactive power may seem beneficial, as it does not consume energy, but during energy transfer, current is truly present. In the real world, lines have resistance, and when current flows through, it causes heat and consumes energy. This energy loss is irreversible and constitutes real loss. Therefore, although reactive power does not perform work, there is energy loss when doing work on other components. So, is there a way to reduce this loss? Luckily, there's a component that acts in the opposite way, the capacitor. It resists changes in voltage. Pure capacitive components have a current that leads the voltage by 90 degrees. It's also a storage component. In the diagram, the green waveform, which is in phase with the voltage, shows the capacitor current when shifted forward by 90 degrees. We can see they are opposites. When one stores energy, the other releases potential energy. When a capacitor is connected in parallel, instead of exchanging energy with the power supply, the capacitor and the inductor exchange energy with each other. Most noticeably, the current in the circuit is reduced, and line losses are also reduced. The advantages are clearly evident. Then how much should we compensate for? Our systems are typically inductive in nature, so. Now let's quickly look at an angle between current and voltage from 0 to 90 degrees, which we often represent as phi. We scan over the current and shift it backward by phi degrees. During this process, some energy is absorbed and consumed, while some is returned to the power source. How much of each? Let's see. This purple current includes both active and reactive components, as everyone probably knows by now. We draw a perpendicular to the y-axis. The red component, in phase with the voltage, represents the active current. Its magnitude equals I times the cosine of phi, which is the power factor. That's something you should be familiar with, the phase angle between current and voltage. We multiply it by voltage, which equals active power, denoted as P. This formula is one you'll likely use frequently. Next, we draw a perpendicular to the x-axis. The blue component is the current generated by reactive power. Its magnitude equals I times the sine of phi. Multiplying by U equals Q, the reactive power. Suppose we keep the active power constant and want to improve the power factor by reducing the angle phi. As shown in the figure, reducing phi, by how much should we compensate with capacitors? We draw a perpendicular to the x-axis. This part represents what needs to be compensated. It involves some simple trigonometry, which we'll illustrate with examples in the next section. By the way, what is everyone's power factor compensation level? Let's discuss in the comments. Thanks for your attention and likes.